The first step is the boot step. This is executed when the system is switched on, and so the kernel code is loaded in memory, an interruption is produced, and basic hardware configurations are initialized. On the boot step, we also start the system access mechanisms, that is the login, the shell, etc. We then have here the usage step. This is the most common step among users. It is where we develop new applications, we work with programs, we execute applications, etc. And so finally we have the shutdown step. This is executed when the system is switched off. On this step we also save persistent information, the stop devices, and we stop all of the devices, the dedicated devices, the shared devices, and also the virtual devices. Now on the boot step, a first piece of software is automatically loaded in memory by the hardware, and this minimum boot code is in charge of the startup for the rest of the kernel. This is very important. This boot code can be loaded from the disk or other device. It also can be loaded from the network that we are connected in. And finally, we can show a list of available options to boot using a bootloader, such as GRUB, that stands for Grand Unified Bootloader. Once the system to boot is selected, it is fully copied in memory. All the hardware structures required are also initialized, and the kernel gets the full control of the hardware access. This means that all of the hardware mechanisms to automatically execute code are captured by the kernel. This means the interruptions, the exceptions, the system calls, etc. Now, when using the operating system, there are two main ways. First of all, using some interactive tools, such as shells or graphical environments. With this, we have an indirect access to the kernel, since the services are requested to these tools. So, for instance, when we run a program X, these tools translate user requests to the kernel system calls, so we don't do system calls ourselves. That's why this is an indirect access to the kernel. This is the most common way of using operating systems among users. We also have here using directly system calls, as we can see on this image. Right here, we directly access the kernel in the terminal. Okay, so we have here these two main ways, using an interactive tool, as users normally do, and also using here system calls directly. The operating system is a software that manages hardware resources, so that it acts like an intermediary between applications and hardware. In any operating system, we have the kernel. This is a computer program that is the main core of a computer's operating system, and generally has complete control over everything in this system. We can have on one side the kernel internals. This defines the data structures to manage hardware and algorithms to decide how to use it. And we also have the kernel API. This offers a set of functions to ask for system services. Now, something very important is that whenever we want to make system calls, these system calls are done by the kernel. So we have here our computer with our operating system, we have here the shell, we have the editors, the compilers, the databases, right? We have, for instance, here a user 1 that uses the shell. Okay, this shell will make system calls. However, these system calls are going to be done by the kernel in the same way. If a user 2 uses a compiler, and this compiler makes system calls, these system calls are all going to be directed to the kernel. Finally, let's discuss what to expect from the operating system. First of all, this operating system needs to offer a usable environment. This means that it will abstract the user from the different kind of systems. It also needs to offer a safe and robust execution environment that will be safe from the point of view of the hardware and also from the point of view of users' interaction. Finally, the operating system also needs to be efficient, so that we can do all of our work efficiently with it. Very well, with this we end this brief lesson and gentle introduction to operating systems. On the following sections we are going to study the process management, that is, what is the concept of a process, the context, the life of a process, the context change, also signals, this is going to be very important, flow concept, communication, and more. We are also going to study the memory management, that is, the address translation support of the operating system. We also will take a look at the dynamic memory and how we can develop a good dynamic memory, virtual memory, and more. We will study these topics and many others in future lessons. We have here 5 different commands. We are given 5 different commands in a terminal executed on a Linux, okay, on a Unix operating system. So let's study all of these commands and their meanings. Let's start with the first example with command 1. So here it is important to know that when we just write an executable like this one, command 1 is an executable file without any arguments. We have no parameters in here. We just run this executable command 1 like so, no arguments inside. Then let's take a look at this command 2. We have here command 2, parameter 1, parameter 2. In here, command 2 is an executable file with 2 arguments. And something very important here to note is that the input and the output data of any command written like this are read and written from the console or to the console. So we have here no files, okay? Imagine we have a file input.txt that we want to run or we want to introduce into our program. If we run it in this way on the example 2, this is not possible. The input and the output are given on the terminal, on the console. However, if we take a look at this example 3, we have here command 2, right? Parameter 1, parameter 2, and we have here this symbol, this character less than, and then we have the input data. Well, with this, we can reassign the standard input by using this special less than character. With this, we are basically introducing that the input for the executable command 2 for this program is going to be given inside this file, so that the input data of this program will be gathered from the file input data rather than from the console. Then, in the same way that we can reassign the standard input, we can also reassign the standard output by using the special character greater than, right? We see here on this example 4, we run the command 2 with these 2 arguments, we reassign the input to be this one, and we reassign the output to be this file output data, so that if we have any prints, okay, inside this program, this won't be shown, this won't be displayed on the console, but however they are going to be displayed on this file output data. So we are going to be introducing data inside this file. Finally, on this example file, it is very important to know that we can connect 2 commands in Linux by using this special character here with the vertical bar. This essentially means that we are creating a pipe. A pipe in Linux is a form of redirection, so that we transform the standard output to some other destination. So we send the output of one program to another. So here from this example 5, the output data of this program command 2 will be the input data of this program command 3.